Hi there, this is a DIY setup of a solar panel system which is charging a lithium battery. This video is to explain the importance of implementing control and isolation and circuit protection even in a DIY system where we've got manual implementation to prevent excessive circuit voltages and currents. We can isolate parts of the system to, for example, change components, and we're doing that through proper double pole switches. We're making sure that there are not going to be any hazardous voltages and currents. We're going to protect cables from overcurrents, and we're going to protect equipment from overcurrents by proper fusing and circuit breaker protection. If we refer to our circuit diagram here, we've implemented fusing and circuit breaking in here to make sure the circuit, the system, the solar system is safe to use. So we have, for example, two 50-watt panels that are wired in parallel, connected in parallel to make 100 watts up here. So for example, what we've done here, we've got two blocking diodes. What are these blocking diodes for? They are to make sure that at night the battery can't backfeed and discharge itself through the solar panels when it's dark. We have double pole switch selection here, so we've got proper control and isolation. So for example, if we want to replace the solar panels, we can switch off the double pole switch here and we can isolate the solar panels. This is a 12-volt system. 12-volt system is extra low voltage. It's deemed to be non-lethal, but that does not mean that you can get hazardous currents and arcing, for example. So just because it's low voltage doesn't mean it is low current. So there needs to be proper isolation in here. So we've got double pole switching for the panels. So for example, if we wanted to replace the panels, we can have proper isolation here that it doesn't affect anything downstream. Switch it back on. We've got a solar controller, which is MPPT, which is maximum power point transfer, which is a more sophisticated solar controller compared with pulse width modulation. We have a breakout box here so that we can add in and measure circuit currents by actually breaking into the actual wiring circuits. We've got an analog meter here to see the battery voltage that's going into the inverter, and we've got a inverter here so we can get AC out, 700 watt inverter, DC in, 230 volts, 50 hertz AC coming out, and we have a lithium battery for storage. We have fusing, correct fusing in here to protect the cables. So for example, if we look down here, we have a 6 amp circuit breaker here, and it's a D type. What we've found with the inverter is the inverter takes a considerable amp inrush. So we ended up through trial and error putting a D-type circuit breaker in there so it didn't trip out when you first switch it on with inrush. So we can, for example, we've got a clamp meter here, so we're measuring the current going into the inverter. So if we switch the inverter on, we can see straight away we're measuring current going into the inverter on the DC side. We've actually got 0.5 amps going into the inverter, even though we haven't actually got any AC coming out. So that at 0.5 amps at normally 13 volts going into the inverter gives us approximately 7 watts just to run the electronics in the inverter. If we switch on an AC load, what we've got here is an 11 watt bulb here coming out, and we can see that we've now got 1.7 amps coming going into the inverter on the DC side. Even though we've got milliamps, 230 volts, 11 watts on the AC side, we've got milliamp loads. On the DC side, we've got 1.7 amp load because it's only 12 volts. In a further video, what we will do is explain the efficiency of the inverter. So to summarize, DC systems do not rely on any internal fusing of any equipment. The cables need to be protected from overcurrents and overloads, so there needs to be proper control gear, proper circuit isolation and proper fusing.